Hey everyone, welcome to our last video in the week 3 series. And in this video, we're going to be working through examples with the normal distribution and the central limit theorem. Before we do that, let's briefly talk about some problem-solving strategy. This is some strategy you may have seen me using in previous videos, but I wanted to formalize it so that you have an idea of what I'm thinking about while I'm solving these problems. So first is we read the question carefully and identify what the problem is about. So this is the general read through to get a feel for what the question is about. We don't have to identify anything here other than to get a feeling for what it's asking about. Is this a probability question? Is this a probability table? Are they asking us about a frequency table or a histogram? What kind of things is this problem talking about? The next time I read through it, I'm going to read through it again, and I'm going to identify everything that I'm given, and I'm going to label it. So this is the point where I start marking up my paper or I start jotting notes down on my homework page. The next step is to start making a plan for solving, and specifically for chapter 6 and 7 problems, you want to identify the problem as a normal distribution problem or a central limit theorem problem. And that's what our previous video was about. Once you've done that, you're going to draw the appropriate labeled distribution, shade the appropriate area in your graph, and use either your table E or your technology to find the probability or the missing values. So the really important part is that setup. Read it carefully, make sure you understand what it's asking about. Make sure you identify all of the information that you're given and that you label it appropriately, and that you identify the problem as normal or central limit theorem, because that tells you how you're going to tackle it. So let's go ahead and work through those examples from our last video. So for example 1, an adult has an average of 5.2 liters of blood. Assume the variable is normally distributed, has a standard deviation of 0.3 liters. Find the percentage of people who have less than 5.4 liters of blood in their system. Okay, so I know find percentage. They're asking about a percentage or a probability. I'm going to go through this again and pick off the information I'm given. So an adult has an average of 5.2 liters of blood. So my random variable X is liters of blood, and the mean for this random variable is 5.2. It says assume the variable is normally distributed. That's good news. And that it has a standard deviation of 0.3 liters. So sigma X equals 0.3. And then it says find the percentage, find the probability of people who have less than 5.4 liters. So now that we've parsed out problem, we've picked out the important information, we've labeled the stuff we know, we're going to identify this as normal distribution or central limit theorem. And we decided in our last video, this is a normal distribution problem because we're not given any sample size. So this is normal dist. We know that our random variable is normally distributed with a mean of 5.2 and a standard deviation of 0.3. We also know we're asked to find the probability or the percentage that a person will have less than 5.4 liters of blood. So let's go ahead and draw that picture. Sorry about my horrible handwriting tonight. I'm going to mark that mean, that's 5.2, and then we're counting by 0.3. So 5.5, 5.8, and then 4.9, 4.6. And they're asking probability that we're less than 5.4. 5.4 is just inside that 1 standard deviation mark. And less than means shade to the left. So I've shaded in more than half of my curve. I know my answer is going to be bigger than 0.5. And I know to find this on a calculator, I want to do normal CDF, or I want to do the normal command on GeoGebra. So for the normal CDF command, we need a lower bound first. And because we shaded to the left, that lower bound is negative infinity. So negative 1 E99. Our upper bound is the 5.4. Our mean is 5.2. And our standard deviation is 0.3. In GeoGebra, we know we want the mean and the standard deviation first. And GeoGebra defaults to area for the left, so I only need to feed it that upper bound. Since I used the TI-84 in the last few videos, I'm going to pull up GeoGebra really quick. So squeeze this over here. Ooh, not quite that big. And then we know in our inbox, we want to type normal 5.2, 0.3, 5.4. If I scoot that video up a little bit, we can see 0.7475. So we can come back down here and say we know this is 7475, or since they asked for a percentage, 74.75%. So we would expect, if the information in this problem is true, that about 3/4 of the population of adults will have less than 5.4 liters of blood in their system. Okay, example 2. The average age of a vehicle registered in the US is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their age is between 90 and 100 months. So I'm asked about probability. So I know this is another probability question. And I know I'm in module 6 and 7. So is this normal distribution or some central limit theorem? So let's pick through the problem. We're looking at the age of vehicles registered in the US. That's our random variable. And they say that average is 8 years. So mu sub x is 8 years or 96 months. And I'm going to write 96 because I know in the next sentence, it says assume the standard deviation is 16 months. Sigma x equals 16. It's important that the mean and the standard deviation are counted in the same units. So if one is in months, the other is in months. You could also take that 16 months and divide it by 12 so that it's measured in years, and then you could use 8 and whatever that conversion for standard deviation is. So it's less important that it has to be months and more important that they have to be matching. So either months and months or years and years. They then say, we're going to collect a random sample of 36 vehicles. So n equals 36. And we want to find the probability that the mean of their age is between 90 and 100 months. And we decided based on those two pieces of information, this is the central limit theorem problem. We know that the sample means should be normally distributed with an average that's the same as the raw data and a standard deviation That is the standard deviation for the raw data divided by the square root of the sample size. So 16 divided by the square root of 36. And we're asked, find the probability that the mean of their ages is between 90 and 100. And we're looking at sample means because they specifically say mean of their ages. So the probability that X bar is between 90 and 100. So just like before, we should quickly draw a distribution. This is now a distribution of X bars. We know that middle point is at 96. And in this case, that standard deviation is 16 divided by 6, which is an ugly decimal. I'm going to pull up my calculator really quick and take a look here. So 16 divided by 6 is 2.67. We want to round it. It's a little less than 3. Because of that, I'm not going to label those hash marks. That's a hard value to count by. But I know it's less than 3. So I know this first hash mark on this side is less than 99. I know this hash mark's a little bit bigger than 93. And I expect that my 90 is going to be somewhere a little bit less than 3, a little bit less than 3, somewhere just past here. And I know this is a little less than 99. This is going to be a little less than 102. So I'm expecting my hundreds probably somewhere in here, somewhere in the middle. Again, notice I don't have to be precise. I'm trying to give myself a visual to get an idea of how much area I'm shading in. And I want to know where I am relative to the mean. I can see from this picture, I've shaded in past that first standard deviation hash mark. So I know my answer should be bigger than 68% based on the empirical rule. I know this answer is going to be pretty big. Okay, so to find that probability, again, normal distribution. So we know we're using normal CDF, lower bound, upper bound, mean, and then standard deviation. And I would strongly recommend that you type it in this way. And the calculator will calculate this and it will leave it in a more exact form so you will get less rounding error. If you are on GeoGebra, you need to use the subtraction, upper bound minus lower bound, because GeoGebra only does area to the left. Also remember that GeoGebra wants mean and standard deviation first. So we'll do that function call for 100, and then we'll do that same function call for 90, our lower bound. So again, I'm going to pull up my GeoGebra window here. Let me clear out some of this extra marking so we can see the screen. So normal, 96, and then I want to do 16 divided by, and then I'm going to make this window big for a second. I need the square root button there. Square root of 36. And then 100. Whoops. And then minus, and then that same function call over again, but for 90. So 96, 16 divided by square root of 36, and then 90. And when we do that, we get 92, 10 if we round that 96 up to a 10. That makes sense because, again, from our picture, we can see that we've shaded in a huge chunk of that curve. We already knew it was going to be bigger than about 0.68, 0.7. 0.92 makes sense in terms of what we've shaded in. So what this tells us is that if we select a random sample of 36 cars in the US, we expect that there's a 92% chance that the average age of those 36 cars is somewhere between 90 and 100 months. Okay, examples 3 and 4 had 2 parts. We'll start with example 3. It says a study reported that children between the ages of 2 and 5 watch an average of 25 hours of TV per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If one child between the ages of 2 and 5 is randomly selected, what is the probability that they watch more than 23.6 hours of TV per week? So I know I'm asked about probability again, and I'm now going to go through the problem, pick out information that I'm given. So study reported, and then we're talking about hours of TV watched per week. That is our random variable. And they tell us that the average is 25. They tell us that the variable is normally distributed and the standard deviation is 3 hours. So sigma x is 3. And then they say if one child is randomly selected, what is the probability they watch more than 26.3 hours per week? Everything in here is talking about raw data, and we are explicitly told it's normally distributed. At no point are we given a sample size, so we know this is just the normal distribution. We know our random variables normally distributed with a mean of 25 and a standard deviation of 3. And we know we're asked about the probability that they watch more than 26.3 hours. So let's go ahead and start with our picture. So this is raw X data. We know that the middle here is 25, and we know we're counting by threes. So 28, 31, and then 22, and 19. And we're asked bigger than 96 or 26.3. So 26.3 is probably right about here. And more than means we're shading to the right. So we know that this is a normal CDF function call. Or if you're on GeoGebra, because we want an area to the right, you're going to have to do 1 versus the normal function call. And I'm going to go ahead and pull up GeoGebra so we can do that function call together. So we want 1 minus normal, and then GeoGebra wants the mean, the standard deviation, and then the upper bound for that shaded area. And we get 0.3324 rounded. And that makes sense because looking at this picture, we've shaded to the right of 26.3, and 26.3 is bigger than the mean. So we've shaded less than half of our curve, something less than 0.5. So 0.3324 is a reasonable value for the picture that we drew. So that means if we randomly select one child between 2 and 5 years old, there's a 33% chance that they watch more than 26.3 hours of TV per week. For this next question, we're going to use that same base information. We know our random variable is hours of TV per week. We know that population average is 25 and that our population standard deviation is 3. And then part B says, if 20 children are selected at random, find the probability that the mean number of hours they watch TV will be greater than 26.3 hours. So they give us a sample size, 20 children, and it says find the probability that the mean number of hours they watch TV. We're asked about a sample average and not a single person's number of hours. So this tells me that this is a central limit theorem problem. We know that the sampling distribution is normal with the same mean as the raw data and a standard deviation that's divided by the square root of the sample size. So 3 divided by the square root of 20. And they're asking us, what is the probability that that sample mean is greater than 26.3? This looks an awful lot like our last question. The only thing that's changed is we're looking at a sampling distribution. And so now our standard deviation is modified. It's going to be smaller than it was before. And we're looking here at X bar instead of X. So let's go ahead and do this on GeoGebra. We know that because it looks a lot like the last time, it's that same function call with a modified standard deviation. So 1 minus, normal 25, same average. And then it's 3 divided by the square root of 20. And then just like last time, that boundary is at 26.3. Ooh, and we get something much smaller. We end up with 0.0263. So if I can, let's close that. That's almost even more than a little bit bigger than a factor of 10 difference there. Because if I multiply 0.026 times 10, I end up at 0.26, which is still smaller than our previous answer. That's a huge difference. That's coming from the spread of the values. So we talked about the central limit theorem. We talked about that smaller standard deviation, but it's important that we kind of see it. If I'm looking at raw sample data, I get that kind of spread out normal distribution. But if I look at that same population, but I look at the distribution of sample means, all of a sudden, all of that data is going to be really closely clustered about that mean. So in that first problem, we were looking at a value that's slightly bigger than the mean. We were looking at about 1/3 of the curve. But if we look at that same position here, it's a much smaller chunk of the curve. And that's why we're getting a much smaller answer. So the sampling distribution is always going to be more tightly packed about the mean. It's always going to be a much narrower bell curve than the original data. Okay, last one. Desktop PC uses 120 watts per hour based on 4 hours of use. Assume the variable is approximately normally distributed. Standard deviation is 6. What is the probability that a single PC will use less than 106 watts per hour? So we know this is about probability. I see that keyword probability. We decided in the last video, this is a normal distribution problem because we have not been given a sample size and we're asked about a single PC. So we're going to go through this problem and pick out our information. So desktop PC uses 120 watts per hour based on 4 hours of use. So they're giving us the population average, and our random variable is watts of electricity per hour based on 4 hours of use. They do tell us to assume the variable is approximately normally distributed and that standard deviation sigma x is 6 watts. So we know that random variable x is normal with a mean of 120 and a standard deviation of 6. And they ask us what is the probability that a single PC will use less than 106 watts per hour. So drawing our picture. We know we're looking at x values. We know our mean is at 120, and we know we're counting by sixes. So 126, 132, 138, and then 114, 108, 102. And we want less than 106. So that's right here, just past that 2 standard deviation hash mark, and we're shading to the left. So we're way out in this left tail, out past 2 standard deviations. So I expect this is going to be small, less than about 2.5%, because I know that 2 standard deviation hash mark separates the 2.5% in the tail from the middle 95%. But let's go ahead and do this. We know our distribution is normal with a mean of 120 and 6. And because it's a less than problem, when we go pull up GeoGebra, we don't have to worry about the 1 minus because GeoGebra default to a less than problem. So this is just going to be normal. And then the mean of 120, the standard deviation of 6, and that boundary value. And we do, in fact, get something small, which is good. That's what we were expecting. So 0.0098. 0.0098. So a little less than 1%. So if we randomly select a desktop PC, there is a less than 1% chance that that PC is going to use less than 106 watts per hour. So very unlikely. So let's keep that value in mind, 0.0098. And I'm going to write that up here before we move on. And part B says, if 500 PCs are selected, approximately how many would we expect to use less than 106 watts of power? So this is neither a normal distribution question or a central limit theorem. It's saying we have 500 PCs. We know that if I move that decimal place over twice, that 0.98% of those PCs use 106 per watts per hour. Oh my gosh, I can't talk today. 0.98% of PCs will use less than 106 watts per hour. And they want to know how many out of those 500 PCs meet that requirement. And I know if I want to figure out how many PCs out of 500 represent 0.98%, all I have to do is take that number of PCs and multiply it by the percent in decimal form, which we already have. That was that probability answer from the last problem. So all we really need to know is what is 500 times 0.0098. So 500 times 0.0098, and we get 4.9. So we're expecting around 5-ish. If we have 500 PCs, we expect about 5 are going to use less than 106 watts per hour. So that question is less about the normal distribution in the central limit theorem, and it's understanding what these probabilities or percentages represent and how we can use them in other types of problems. You're not going to see those on your test this week, but I thought it was an interesting question for you to see in case you encounter it in another situation. Okay, so that's a wrap on week 3, the normal distribution and central limit theorem. If you have questions, I have office hours Thursday from noon to 1 and 7 to 8, and I'm always available via email or text message. I hope you have a great rest of your week, and I'll see you in our next video.